Good morning, everybody. So we're back again. Today we're gonna talk. So we usually want to make this a more regular thing. So I don't know. It's been like 2 months almost since the last time. That's not really the plan. The plan is to have it once a week, and we'll try to be better at it. Now we're trying to get streaming stuff down as well. So if you're not watching this live, then hopefully it's Sundays at 4 p.m. Eastern European time. I have no idea which is. It's GMT +2, so you can calculate your own time from that. But yeah, we'll try to be live every Sunday. That's our goal. Continuing on from this. So today we're talking about the paper from Intel. The title of the paper is Tabular Data. Deep learning is not all you need. Its premise is simple: is that deep learning is not ready for tabular data, at least not yet. We'll see if that changes. And today the MC will be Hendrik. So for those joining us the first time, my name is Joosep Kivastik. I'm a PhD student at University of Tartu, where my topic is optical systems for nanosatellites. And with me is Hendrik, who will introduce himself, and he will also take over the paper talk for now.
Okay, hi, I'm Hendrik Gervais, and I focus my research currently on autonomous robotics. Mostly off-road autonomous robotics. So let's get into the topic. So first off, as Joseph already introduced the basic premise of the thing, I think the interesting thing here is also the larger historical context, which is kind of the tabular data has had methods to deal with it for longer than, let's say, other types of data like image and stuff like that. So the let's say the algorithms, some examples of them are random forests and different basically decision tree like algorithms have been solving these problems quite well already for a long period of time, and there hasn't been, let's say, some rapid increase in performance over the latest this kind of machine learning boom. There has been some improvements, and all of these comparisons with neural networks are made with these let's say improved tabular data algorithms, which we will talk about a bit also. But let's say big picture wise, the improvements have been mild, I would say, based on these articles. But when we get to the numbers, we can talk about this a bit more. Anyways, so first off, what is tabular data? It's pretty much everything you can represent in an Excel table where you have rows and columns where, for example, the rows are classes and the columns are attributes or some data for each class. And the goal of the algorithm is then to predict, for example, the classes. Yeah, tabular data is pretty much everywhere. Most of, let's say, data that companies gather is tabular data. So definitely a very useful field of machine learning, and it is quite interesting that there hasn't been any explosive progress from, let's say, deep learning algorithms here. And we should think about a bit why that is. Here we have some this was pretty much the abstract and the intro. The main conclusion of this first paper, we had two papers today. One is deep learning is not all you need, and we have some quick references from a survey paper also, Deep Neural Networks and Tabular Data, which does some additional comparisons and conclusions that I will reference too. But the main conclusion of this paper will be that there isn't that the, let's say, the deep neural network approaches, which also try to solve the same problem, perform similarly to the conventional algorithms, is what I would call it. So the main thing is, let's say, all approaches are very similar. Even within this tabular data algorithm space, all of the approaches are quite close to each other. Yeah, and so there are some limitations to that statement that I will get to when we get to the second half of the paper when they discuss results.
But the article itself says that to the extent that gradient boost tree outperforms all the deep models across the datasets.
Yes, and additionally, they did the neural network and gradient boost algorithm combination, which, well, first off, the decision trees plus, well, some kind of tree search and trees in general plus neural network working together has been a thing for a long time. Not here, they used it quite differently than some other, let's say, approaches used. But let's say AlphaZero and stuff like that also use neural networks plus trees, basically decision trees. But they do a different. Their tree structure is different, of course, and the algorithm there is Monte Carlo tree search, not what we're talking about today exactly.
And also, I guess a bit of a spoiler, but I think the statement that our study shows that it outperforms is not true. I would say. I mean, it's kind of funny that they say they also in here they say, so if you get how this paper is structured, then they took different deep learning algorithms that have been used on tabular data, and of course every time you write an article you use some kind of data sets, which most likely are the best performing data sets. So they took those data sets for each of the deep neural models that they were using, and here it says so you would guess that the neural network is better on the data sets that were used in the original paper and worse on other data sets. But here it says that it's better across the data sets, so it's better on all the data sets kinda, and also better on the data sets that the deep models were, let's say, optimized for, in a sense. I think this is just a false statement.
Yeah, I agree. It's like, but it seems like it comes with the field, because the field is not progressing at all. So every, like, if you have some like incremental small step and you see that there is something that is statistically significant, which I will complain about later. So they are like, oh, we found something that is statistically significant, so it is better. But yeah. Anyways, another big thing why to use these conventional algorithms is less compute and basically more explainable models. So these, because you can, if you have a decision tree, you can pretty much just follow and understand what inputs with does it take and why does it predict what it predicts. So I would say that is actually quite an important part of this. They are kind of explainable-ish compared to neural networks, because let's say the amount of connections is not ridiculous.
Yes.
Having said that, let's get into some more detail. So first off, tabular data algorithms have kind of two main approaches, wondering if I didn't copy anything specifically for that. I won't go into the deep neural networks yet. tabular data algorithms have two approaches. One is basically random forest-based approaches, where the decision trees are first initialized randomly, and then basically the best ones are chosen. And the other ones are these gradient boost algorithms, which are the ones, which is one, for example, this XG boost, which slightly outperforms the random forest algorithms. I say slightly because to me it is surprisingly slightly, but someone else might disagree. Be like, oh, we got that 2% up, and we're like, yeah, very proud of that.
Don't you know the
in
story?
20 years.
The story about the British cycling team.
No.
Because I'm currently reading Atomic Habits, which is a fun book. It gives me an existential crisis every time I read something self-help, something related to self-help. But anyways, the story I've heard before is a story about how some years ago, 20-ish years ago, there was a British team. They were the worst team. They were so bad that some cycling companies didn't want to give their bicycles to that team, because they thought that they would reflect badly on the bicycles. But anyway, they got a new head coach, and his let's say methodology was that 1% gains in a lot of areas in the end create a huge effect. Which, and they won a lot of things after him. The funny part of it is, of course, that there was doping involved as well. But I mean, I guess that is kind of moot, since everyone is doping and cycling anyway. So I don't know if that actually matters or not. But at least they like their asthma medication a lot, so to say.
Maybe they didn't have doping before.
Don't.
Anyways, I agree with that premise, but still, let's say the timeline is quite long, and I would say there's still something here that is, say, definitely something to be figured out. Let's say we are quite good at solving some tabular data problems, but we are definitely far away from perfect, and we have not been converging to becoming a lot better. While most other papers that we are looking at, we have to compare papers within 2 years. Otherwise, it is like old information in the papers, pretty much, because everything is changing rapidly. The main point here is this: nobody has kind of cracked this part yet. I think that's interesting, but yeah, I agree otherwise. So, but yeah, overall, gradient boost techniques and random forest approaches, gradient boost techniques outperform. It's those algorithms came along roughly year 2016, so still relatively recent innovation. As before that, there had been also kind of a larger random forest time. Okay. On the deep neural network side, there is one larger problem with deep neural networks, which is that so the kind of, it is hard to make the tabular well. Actually, I want to start from that side. Basically, you can't take decision trees themselves as an input to the neural network models, because the classical decision trees themselves are not differentiable. But this problem already kind of is, this is a problem that has been solved. So this is not a fundamental limitation for the neural network approaches that want to use the trees themselves within the algorithms. But the much more recent and larger approach is basically attention-based models, so transformers and such, or transformer-like models used for tabular data. And the last important keyword on the theory side is ensemble learning, which basically means that you have different algorithms or different subsets of algorithms, basically. So for example, single trees or different machine learning algorithms working simultaneously, and then the output is combined from all of these different models together, and some usually weighted by their validation loss during training. So that's a way to get some extra performance by combining the strengths of different algorithms. Yeah. And ensemble learning is also the method they use to combine the neural network approaches and the XGBoost approaches. Which is interesting to me is that ensemble learning doesn't seem to be something that we usually see that much in regular neural network papers, which as if
I think there is a lot. I mean, I think there is a lot of ensemble learning actually. Maybe not in papers, but I think in the real world there is a lot of it.
Yeah, but it's like it's interesting that nobody comes around goes like, but if you take these two different neural network approaches in an ensemble and try to kind of somehow estimate based on some loss functions, what would be the actual correct one or the confidence of the prediction or something like that. But yeah, I do agree. It seems like something that would be done in the real, let's say, quote unquote real world versus academic world, where you need this robustness as much as possible.
Yeah, there are also, I know, like different. Yeah, I mean, I at least know that there are different ensemble methods that are looked at. For example, there is a method where you have multiple inputs and multiple outputs, which is interesting. And yeah, there are like other. Dropout is kind of like an ensemble method, for example, in a sense.
Yeah, I mean, you could argue that neural networks kind of do it within itself, and then you can take the outputs and somehow filter or try to validate those outputs. Or if the first prediction doesn't work, maybe take the second prediction, etc. But still, it's not two different neural nets.
Do you have cancer? No. She died of cancer. I guess the second option was correct.
I did not mean with binary classifications, but let's say with image classification, it's much easier to think about. Maybe it's this primate or if it is not this primate, maybe it's another primate, for example, and go through. But it's more unlikely that you have totally different, let's say, jumps.
Yeah, because actually it's with image recognition, it's usually always to look at like whether the guesses like in top 5 or top 3 of the guesses.
Yeah. But I would still claim it's not exactly the same. So approaches here seem to be a bit different, but not radically. So, but it's still let's say, to me it was interesting to read about this, as it seemed that it wasn't particularly difficult, and it was a bit surprising that it is not used as much as I maybe would have expected in papers, at least that I have seen.
Yeah, or we just don't know the actual most of the papers.
That is also true, but we'll see. I will be if we look through more papers and we start seeing it more, then I'm happy to be corrected. Let's put it like that.
So next time GPT can't get any bigger. It will just like train 10 of the biggest models and do an ensemble.
You do 10 different GPTs on different datasets, and instead of putting everything together, and then you have voting between the outputs. For example, that would be ensemble learning.
It's like a committee. You have the know-it-all on Wikipedia, you have some scientific dude, and then you have some, I don't know, whatever, different archetypes.
Yeah, to me it's interesting with that kind of approach scale better, but I guess that's kind of the good old neural network approaches when initially people did try to make these specialized networks and then combine to the output. But this, I haven't seen papers in that direction for a while, at least to be like we have conquered the world type of papers, but maybe definitely they are out there also. Just haven't kind of seen anything myself. Anyways, their main, let's say, comparison points are accuracy, training efficiency, training and inference efficiency. So what's the performance? And then last one, short optimization time. So fast hyperparameter tuning, which this will be my rant about the paper on what the heck, why did they need to include that based on the results they got, but we'll talk about it when we get there. But yeah, classic, perform fast, perform accurately. And the third one is them wanting to make more in the paper. So first off, it was explained how they did the hyperparameter optimization. So to me, it was this part was already kind of interesting, because initially based on this sentence, I got a different kind of let's say understanding of what was going on than from the actual results. So to me, this sounded like that they basically try to vary the they're basically trying to search in the hyperparameter space and kind of find the optimal parameters within that space. There are some questions here, but mostly each model that they trained, they did this hyperparameter optimization, which I think is very important and good. But at the same time, this also might mean that the hyperparameters that were chosen might not be the same or are very unlikely to be the same as those that were used in the original papers. So the hyperparameter optimization becomes a very important part when comparing the results. And it is likely that all of the algorithms don't kind of like the search and how it is done is a very kind of critical part of this, how well these algorithms perform, especially when the result differences are so small that it is can be kind of hard to evaluate which one is actually better or worse. I will quickly scroll to the hyperparameter optimization plot to explain what my kind of me being surprised here. So if we look at this hyperparameter search, then it seems that it already converged with all of the algorithms. Search already converged with about 100 iterations, and then the loss was stable from there onwards. So it begs the question: is it actually like the kind of the global minimum of the hyperparameters? Or should they have, especially if they spent 1,000 iterations on this, maybe they could have done some more interesting searches, as I don't think it is necessarily true that you can converge the hyperparameters like that. The second part is this interesting question of which of these algorithms converges the fastest with this hyperparameter optimization?
Tell.
I would say they all equally do it equally quickly. But this is like they stated this as some kind of a major point in the paper, as somehow this XGBoost is specifically different here. But there is no way. I mean, if you can see my cursor, then roughly all of the algorithms have converged almost at the exact same time. Maybe there is a range of 50 iterations, maybe, if I'm being generous. And it seems like the only difference is what initial hyperparameters they chose. So if they wanted to say that they converge at the same with the same kind of speed, then they should have chosen the initial parameter so that the losses would be the same if they compare the loss graph. So to me, that's like there was statements about this conversion speed in the paper which made no sense based on this graph, or at least this graph doesn't agree with their statements in the paper. I would go this far.
This like, wouldn't be the first statement that doesn't agree.
Yeah, but it was so weird. But yeah, so to me it felt like they kind of had the theory that it will converge faster, and they had this a bit of a selection bias here, where they saw this graph and saw that it was smaller, quicker, I guess, or I don't know, but I'm pretty sure it is kind of a misunderstanding of that graph there. Yeah, that was the hyperparameter optimization overall. At least it's good that they did it, I think. So one big part of the paper is that what they commented is there isn't a very good way of comparing tabular data results compared to many other, let's say, fields in machine learning, where there is quite strict ways of how to compare, so with each other. But let's say I was kind of confused about these sections of the paper also. I was that you can't just compare, for example, accuracies overall data sets or something like that. Yeah. What did you think about the optimization process part?
I was just reminded of a paper I read. I was wondering if they use some kind of hyperopt based on Bergestra and others, which is a Python library for model selection, hyperparameterization, optimization. I was wondering because I know there is this dude that I read a paper on that talks about how to choose, for example, learning rate for deep neural networks. I was wondering if it's the same guy, but I forgot to do the search before, and I was trying to do it now. I found a paper. This is referencing, of course, but I didn't write the paper I wanted to find. Mm-hmm. Anyway, yeah, the graph was funny. Otherwise, I mean, hopefully it makes sense the way they optimize it.
Yeah, they made the point that the original neural networks perform well on their given data sets, and they have most likely kind of either optimized the hyperparameters or the model architecture to those data sets. So that was their main reason why they claimed that the neural networks are worse, kind of, compared to the XGBoost. But yeah. The other part was the statistical significance, which they had in their comparison part. They want to claim some statistical significance here between different methods. I don't know. I would say that most of it's very hard to claim this because of something called, well, basically the data samples versus kind of how the sample are chosen from the like the population of all possible samples. It is like most likely all of the data you have in your input data is not representative of all possible data you can have, basically.
That's why there's calibration issues and drift and everything.
So I think from there, I think that's the reason why it is very hard to claim in this machine learning space, like statistical significance between different results. I think it's kind of naive to, this is, in my opinion, a bit of a naive approach. And I would say that is also a reason, like you could argue that, let's say most machine learning papers compare results based on accuracy. And they just say that I have now 2% better accuracy. Most of them don't try to claim anything about statistical significance or anything like that, because they know whatever, let's say, plus minus they give to that percentage will be bullshit, depending on, basically the bullshit comes from the fact that those models don't generalize to the whole possible data inputs. So you might get a very different result on a different data set. If it is trying to solve a related or a bit different problem. Yeah. Here we have a good example of that, where these are test results on tabular data sets where the models are the same, but the data sets are different. And obviously these perform very differently on different data sets. But fundamentally, like, it's not like they are fundamentally different data, like if all of them are trying to solve tabular data problems. So yeah, to me it was a funny part about this paper. But yeah, continuing on, that's
the funny part with each paper for
yeah, maybe pet peeve type of thing.
Yeah, but the main result basically shows that the neural network models do well on the data sets that they were optimized for, or should work best on. Basically.
Yeah, but important part about these test results, I have no idea how well these perform. Because the metrics they used are not very good, in my opinion. They aren't comparable between different data sets.
How would you do it then? It's only easy to criticize.
For example, the same way they did in the other paper.
Okay, what did they do?
Trying to in some context try to project it into some kind of accuracy or something like that. But here they already also have mean square error here. But my problem with this mean square error, it will be harder to define a good, let's say, accuracy metric, because it starts let's say it is sometimes important how close you get to the correct value. So it becomes kind of, this is the problem in this space. It is hard to come up with good metrics. But the problem with these mean square error metrics is that you can't compare two mean square error metrics with each other. I can't take this California housing thing and from here estimate how big of a potential error I might have in another data set, basically, because I would have there is no, let's say, connection there.
Yeah, so for example, if we go back up to the, let's say, original paper, we don't know how much better is, for example, with the I dataset, XGBoost is like seems to be a lot better than the others. It's 56. The next one is simple ensemble, which is 58, and then all the neural networks are at like near 70. So how does this compare to something like gas, where the errors are smaller, the differences are smaller?
Yeah. So, yeah.
Sorry, can't you like normalize it somehow?
Well, the problem is that yes, you could normalize to some kind of percentage and how much it improves compared to the last good result or our last best result. But then you can get percentage that it's like 200% better than the. So you can normalize it based.
Because they did something right. They did. I don't know if you copied this part, but if you go in the paper directly behind it, they went for to directly compare between the different models. We calculate for each dataset relative performance of each model compared to the best model of the dataset. So they have they compare relative performance between. Yeah, right there.
Yeah.
Up. Yeah, so average relative. So this is the table. So this is like average. So what they did.
Yeah.
So they compared with each case to the best performing model, and the average difference from that.
But I think here they compare how much worse will it get on unseen datasets. So stuff that it wasn't trained on. So basically, so how much worse is it on?
No, not trained on.
Sorry, not trained on, but the.
No, actually, so maybe you were correct.
Isn't it?
Sorry, maybe you were correct. I was sorry. But it's really to use a data set you haven't been trained on, right? With tabular data. I would say, maybe is it untrained or is it not optimized for? Let's say, which one is it?
Models unseen data is not a data set it was not trained on, but a data set that did not appear in its original paper.
Yeah. Yes, that makes more sense. Because with tabular data, because every time we might have very different data.
Yeah. But it's basically they mention a few data sets in their paper. Usually, each paper mentions a few, and then what they show here is the data sets that they don't mention. These models perform worse on. So, which is quite an interesting result, in my opinion. So it's basically we didn't show the results that were shit. That's basically what this means. Sorry if I misspoke before. That's what I meant. But yeah, sorry, I should have also put that because it's also another funny result. I had text about this, I think here, but not the graph, which I could have added.
Yeah, so overall what we see is if we talk about singular models, then simply SG boost is indeed the best, but it's not best in everything. Like I think the abstract gives a bit of a wrong understanding. You might read wrong. It's like from the abstract, I could have read XG boost is like simply the best in all of them, but it's like averaging the best because it's sometimes second, sometimes third, sometimes fourth. A lot of times it's first though, but yeah, it's not always the best.
Yeah, and interestingly, to me, the interesting result was also that all of these results are quite similar to each other, with many data sets, and in some data sets there are quite large percentual jumps. So if you look at here, 2.18 versus 1.44, that's like a 30%, let's say, lower error, which is significant, quite like a significant jump. While let's say on this spot, it goes from 55.38 up to 56. Okay, there is one that is performed significantly worse, but that seems to be this DNFnet seems to perform quite. This DNFnet kind of makes the comparison weird because it seems to solve some problems really, really well here, but then it's quite bad on all others. So
yeah.
But yeah, overall, interesting that it is these are quite uniform. It is interesting that basically the deep neural networks perform very similarly to the classical methods at this point in time, basically. I am not sure if that means the machine learning methods have caught up, or it means that there is something more fundamental that going beyond this part is the hard, basically, step that needs to be taken. Although, based on these results, I would say that it has converged to something very similar to each other.
Yeah.
Yeah.
Also, I wonder how much research goes into this.
Yeah. Well, I would assume it's an interesting question because I would say the demand is there from outside of academia because there are a lot of these data sets, but because there isn't like a lot of improvement paper to paper and hard, not as easy maybe to publish. Therefore, that means that there are bad incentives for academia to pick up research here. So, which also comes back to, well, this is Intel's research. But that, to me, still the coolest part about this is I would have assumed machine learning, like neural network approach, perform very well here, but they don't.
Yeah, I actually knew nothing about this as well.
Yeah, because I think let's say some basic machine learning tutorials, for example, this fast AI and stuff like that, do quite a bit with tabular data. So that means this is this default use case. You probably perform quite well here, but no.
The question is, can you make an image out of the tabular data? Then you can do CNN, then it works. I think
take an image of your Excel page.
That's what I mean. Basically, an Excel page can be an image as well.
Yeah, but realistically, it also does mean that the tabular data, classical and conventional algorithms perform quite well. Also,
I mean, everything has its place. It's another place because also neural networks are more computation hungry than, let's say, regular methods. And you always have to make the choice to see what makes sense. If you can do it with linear regression, then why use anything else? I mean.
Yeah. Yeah, and well, their novel algorithm, kind of, which is the ensemble between neural networks and this decision trees, seems to perform quite well, and more importantly, quite stably well among all the problem spaces. So probably they're quite happy with that.
I think most likely neural networks do some stuff like that's why we have deep ensembles, right? So every method has its own strengths and weaknesses, and as you can see with the for example, with the I1, with the because SG boost is the best there, and without SG boost, the deep ensemble is shit. But if you add SG boost to the deep ensemble, then it's very good. I wonder if any times SG boost makes it worse. Once in Epsilon, actually adding SG boost makes it worse. So might have it that because SG boost is quite good generally, then it has a low validation error, which means it has quite a high effect. Can you do that? So
1 second, my battery mouse.
Because as we see, SG boost is itself worse than the deep ensemble, then it has a negative effect on the deep ensemble with SG boost. It's actually fun. That's interesting actually. The deep ensemble without SG boost is 1095, but if you add SG boost, it is actually worse than SG boost alone.
Yeah, the numbers here sometimes are, let's put it like, let's classify them as interesting. I also saw in many parts where the ensemble combining the ensemble with XGBoost and without XGBoost, the results are manipulated in an interesting way. Like the weights that are found are most likely they are significantly different between those two. So the weights of different networks in the ensemble basically change. Not only, let's say, not only they just add one, but all of their relative network weights change, and that's why it is different basically. So basically, in the epsilon part, because adding XGBoost into this ensemble probably increased the weights of some other networks here, which had a lot otherwise a higher error, which caused the total error to go up.
You think
is
so?
How I understood it.
I would I mean, relative weight should have decreased, right, if you had another model into it.
Yes, but the relative weights between the neural network approaches, I would assume that changed somehow, but that doesn't make
Why?
sense.
That doesn't make any sense. They should be because I think they talked about how you can put ensembles together, so you can have each of them have like the same voting strength, or you can base it on validation. I don't know what did they do in the end. I don't remember. Did they say?
Validation, I think.
Because I remember reading it. It says like you can do this or this, and then I don't remember what they
I
actually
don't think
chose.
they say, but
okay. We used entire training data set to train each model. No, not that.
I don't think they say.
That which is funny.
Yeah, but I'm assuming with weights, because that's the classic. You first define the general one and then the specific one, and which you usually use. I don't think you otherwise would have that equation too.
Well, this is more not general. The first one is actually the
Anyways,
more specific one.
It's a validation loss for the model.
Yeah, so it.
So it doesn't change.
Yeah, XGBoost should have a higher, higher.
So if let's say we have a how is that possible?
Maybe they retrained when they did Ensemble. They retrained the models, and then you got like so that it's not like directly comparable, which would be weird. Or they used the worst versions of some models, or they used all of the models.
No, but they have plus minus one, ni minus two. I'm not gonna go there. That's like also another rant, which yeah, no reason to go into that rant.
But yeah, okay. Anyways, they don't really specify how. I think they made. I know. I mean, they will talk about ensembles soon, but I think this.
I agree. Yeah, but still, I agree with you. I don't see how that's possible.
I didn't say it's not possible. I said it's interesting.
Okay, I will take it further.
Do not misquote me.
I agree with it. It's very interesting, and I don't understand how it can happen. In my the way I understood the validation part, the ensemble part, and these results here.
Mm-hmm. But yeah, so they didn't say how they created these ensembles, but afterwards they did say that they wanted to see how efficiently can you build that deep ensemble, which I think was a nice addition to the paper. What are you looking for?
No, we're just hoping to find something that explains it in a bit more detail, but I don't think I will find something. Anyways, but yeah, here they describe this relative performance chart, which we covered a bit before. They bring out two reasons why this why this can be the case. One is selection bias, the other is optimization of hyperparameters to those specific networks or those specific problems. Sorry.
So yeah.
Having said that, if it is the optimization of hyperparameters, then it would mean that their optimization of hyperparameters that they did here is not, let's say, complete.
Yes.
Yeah. There was also another cool sentence that I skimmed over, by the way. Basically, what they did is they trained, they continue training each network until there are 100 consecutive epochs without improvement on the validation set, which to me was very surprising because isn't like early stopping recommended?
Yeah, so I was also thinking about this. Is that was it in the case that they didn't have any divergence from the training set and validation data set? Maybe they somehow had magical training system where they only converged to a point and then kept steadily going. I don't know.
Maybe. But I guess if you look only at the validation set, it's at least it's not fundamentally a problem because like you will start overfitting to the training set, right? And
yes.
But the validation set without improvement, it can still be the case. But I guess their main goal of this early stopping is to make it so it doesn't start getting worse on the validation set.
Yes. But it's weird.
Yeah.
No, for example,
to me it seems
because I mean, this still can be the case because they didn't say it doesn't get worse. It says no improvement.
Yeah, but I don't think they were like, it goes worse, putting it in the paper.
We had 100. It says 100 epochs, so we're going for 100 epochs.
Yeah, fair.
That would be funny if they did it like that.
I mean, to be honest, that can happen quite easily. To make all of them have to look the same. So let's do everyone the same. Doesn't matter if it makes some worse. Was funny, interesting to me. And even if the validation set is the same and the training set goes down, you might still be overfitting, even though, like, especially from a generalization point of view, it might be fine on that data, but it might not generalize as well to, let's say, if you put new data in or more data in.
Because
so
I
still, yeah.
Because I was wondering, because that should be the same when you're training. Maybe they did, or I don't know. So I don't remember. How do you train decision trees? When it's just, there's a concrete endpoint, right? Or
what do you mean concrete endpoint? Like what's your loss, do you mean? Or...
I mean, no, at which point the training stops?
You mean in the XGBoost option?
Yes.
I don't know exactly. Okay. I think it also minimizes a loss, and then it says it's now it is done.
Okay.
If it's under some loss, or it basically runs into the same questions, more or less.
Okay, I was wondering it because if it doesn't, then maybe it's just like some doesn't know how to train neural networks, and that's why they have this in here. Not like I'm good at training neural networks, but at least from what I know, this is a weird statement.
Yeah, to me it was also weird. That's why I pointed out. But at the same time, I don't think necessarily it could also not have had a large impact on any of the results. But based on the fact that they had, let's say, a few surprising results, I would say it is also kind of weird. Then there is also a paragraph how this graph says a lot of things, but I already laughed at it a couple of times. But there is also the important part here, which is that this testing different hyperparameters. So the number of the iteration time was a lot faster for XGBoost. So they were able to actually do it faster, but not with this graph,
Yeah, because they were actually talked a lot like how do you compare it, and then they chose and okay, we'll compare it to iterations for a few reasons. And then
yes, but now the iteration but they still went with it because they did this comparison, and obviously they know that the XGBoost is faster. So now they want to somehow say it because they were there, they did this thing, and they most likely got a lot faster results. So I actually think that they chose a really bad graph. I don't think the result is wrong.
Yeah,
it's just very funny.
They should have just skipped all of this text on why they're choosing iterations and just gone with, I don't know, flops.
Yeah,
because I don't get why you don't go with flops.
Basically, I agree because you can do the hyperparameters is like amount of dimensions, right?
Yes.
Pretty much, and you would expect it. So the question is how the first question is how long does it converge in the hyperparameter like in these hyperparameters? But the second question, which they actually point here, is how long does it take to calculate one of those iterations? Mm-hmm. But now they somehow forgot this from the graph.
Because their only statement is however each, so they say that flops are suggested, but each hyperparameter set has a different flops number, which is a funny thing to hear, like flops number. Anyway, so it is impossible to compare different models. So we're not. Why? Because I think this is the exact reason why you would be comparing flops. Because then you
not time.
Yeah.
Otherwise, you could compare time.
Yeah, because I mean, I get why you don't want to compare time because it depends on your hardware, but flops is hardware independent. What?
But even if you have the same hardware, they have this optimization point, but flops doesn't get over the optimization point. So I'm like, what if you do flops and you have a shittily optimized program, you get time and flops become equivalent on the same hardware.
Yes.
I have even more questions. Anyways, I just think they kind of didn't wanted to put this in, but it just doesn't make
sense. Okay, it's interesting. Actually, it shouldn't be floating point operations per second. It should be just floating point operations. Flows. That would make sense. How many floating point operations you have to do? Oh, okay, then also optimization is a part of it, but not per second. Because I mean.
Yeah, I agree with that also.
Anyway.
Yes, first off, should be to me it seems like they wanted to do this comparison, didn't work out. Then they tried to explain why they did this comparison incorrectly, which is but then they wanted to publish the paper and get done with it because this result was not significant. So they were like, that's fine. Throw it to the reviewers to eat.
Because to be fair, we don't know what changed between this, because this is a preprint. If you want to read the actual one, it's on Wiley. Actually, I can check if I have. I would have to change. I would have to change VPNs.
I can do it. I have a trick.
Okay,
which is not piracy, by the way, so I'm good.
Yes. It's through our university library.
Yeah. What was it though?
What was the name of the paper?
Can you link me the
sure.
Paper journal link?
Yeah, I will put it to Discord. Put it. It's ACM, not Wiley. Anyway, I don't know if it says Wiley somewhere. I don't know if we have access to this one.
Yes, we do.
We do. This only has one citation.
I think wait, what? If the search wasn't that bad, then what? Okay, this might take too long to get.
But do they still have the same graph?
Sorry?
Do they still have the same graph? Oh no, did you get access to the paper?
No, I didn't, because of reasons.
Okay, this it's not useful time looking at Henrik clicking. Next time we should do this. We should say that next time we will
just in case,
actually look at origin, not only the preprint versions.
Yeah, should do it just in case.
Because I have like
usually
I have 10 minutes after which I have to leave.
Yeah. Okay. That's fine. Let's go through the more interesting parts from the. We did get through with the original paper, and the conclusions are already what we discussed about.
Yeah, the only thing I highlighted from the conclusion was, in our analysis, the deep models were weaker on datasets that did not appear in the original papers. That was almost true, and they were weaker than XGBoost, the baseline model, which was not always true. Therefore, we proposed using Ensemble typo, which XGBoost. This Ensemble performed better on the datasets than any individual model. This is also again not completely true, which is weird. Why do you make like concrete statements that you can reference your own paper, which this is not true? It's like almost true. It's like you can say it's mostly better. Everyone's okay, good. That is, it's better when it's not. Anyway,
I would claim it is more robust. Would be the wording I would use.
Yeah, sure, makes sense.
That was the thing I was impressed about. It was more robust. Let's say, but I agree. The far-reaching conclusions are annoying when they are not true.
Yes.
But yeah, that was the paper. Overall, interesting point. That but I'm surprised about the citation part, because the next paper we have does cite this paper.
So maybe this is the one citation.
Yeah.
Let's see. Total citations 1. So I get it cited. Nope. So maybe this web page isn't the best because it's some other paper.
Yeah, seems broken. Anyways, the next survey paper basically has the same conclusion, which is my main statement here, that deep neural networks perform similarly to classical methods. Classical methods often perform a bit better. But overall, everything is quite similar to each other. And we can also see, I think here it is also cool to see some of the older approaches here. Just decision tree, linear model. So K and N. I say older, but not because it is worse, but it is comes back to my original point of the development of these algorithms in general, or like how much better can we solve tabular data compared to let's say 10, 15 years ago. Although most likely some training improvements have been made, so we are able to get better results, but we train them a bit better. But yeah, there are some conclusions which I think are interesting. One is decision tree ensemblers are still state of the art. So if you need to pick a tool to solve tabular data problems in the real world, it is more likely easier to set up this decision tree algorithm. You need less compute, possibly less data, not sure about that. Although in tabular data, often your data is although not most likely, if you are Google, you think this that statement might not be true, but it is a very important statement. How much data you can take in during for training one thing. They also brought out the same thing that this paper brought out, which is the abstract 7. Which is that unified benchmarking is not there yet. They tried to unify this a bit, but they also brought out that this needs future work. Their main point here is they should have an open benchmark, which algorithms can compare against, which does exist for many other machine learning fields, which is once again, to me, quite interesting. They also brought out that pre-processing can give a lot better results and is an important part. To me, that seems weird. If you say that pre-processing can make something work better, then the question is, why don't you do the pre-processing? They bring out the different architectures, the transformers, and basically this smooth decision trees here also, similarly to the previous paper. Regularization, just deep model specifics. Once again, here is an interesting point which I didn't quite get, is that they said that they could use generative models to generate data to train on. I don't believe it, but it was interesting.
If you can create the data, which is very good, then your model should already be good enough to
invert your matrix.
Yes, can.
Unfortunately, life is not that easy, but let's say if you're
just create a neural network that is invertible. Only diagonal matrices.
Well, if you can backpropagate, then you can go the other way around, right? Funny. They also commented the interpretability here, which, as I mentioned before, is a lot better for the conventional methods and not as good for the deep neural networks. But yeah, and then evolving data streams. Yeah, I'm not sure what to say about that.
Can you explain what is an evolving data stream?
Evolving data stream means that the way that data comes into this to these similar problems that are usually solved by tabular data is changing. So it becomes important how you get the data into that tabular form, and you might be doing already some processing to get that. And they also point out that there is limited data resources usually if you want to deploy these models near the data streams. So let's say you have you might have some only limited compute in an area where you actually want to run these algorithms, for example, a mobile phone or something like that. Yeah, I didn't spend too much on talking about thinking about these open research questions. So if you don't want to say much about it, then we can also end.
To be honest, I didn't read the second paper. I presumed you would read it because you were the host today. I was seeing if I can get something interesting out of it.
It was mostly the same, which is, I think, good because the main conclusions were validated, but there wasn't also nothing necessarily. It was a survey paper, so with survey papers they kind of collect a bunch of papers and try to make their own conclusions on the different sets of papers and also propose open research questions. But yeah, the open research questions were let's put it like that. I didn't also think about them too much. If they I don't have enough context or let's say pre-existing knowledge to think anything about them. Are they good or bad?
Yes. Okay, I think then that's all. So in conclusion, neural networks are not yet that useful for tabular data. Maybe someday. So if you're using tabular data, then be sure you use the appropriate easy model, maybe. Unless you have a very niche case where you can use a neural network.
Yeah, and unless you also kind of are trying to get that very last percentage for whatever reason, then it seems like all algorithms perform quite similarly to each other.
And then just use them all, and then
yeah,
Ensemble. Okay, well, thank you for joining us. We haven't decided what the next paper will be. We will see. But yeah, we'll try to be here again next Sunday at 4 p.m. Central European time, no, Eastern European time. So whatever time is in Tallinn and in Helsinki or copied in Cape Town, that is the time.
I think Turkey also, right?
Yeah, in Istanbul, I think as well. So whatever time is there, whenever it's 4 p.m. there, then that's when we'll try to be here. We'll try to be better each time. But thank you for joining us. If anyone ever sees this, but yeah, see until next time. So now I will stop.